Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 11, Part 3. Suppose a fire insurance company wants to relate the amount of fire damage in major residential fires to the distance between the residence and the nearest fire station. The study is to be conducted in a large suburb of a major city. A sample of 15 recent fires in this suburb is selected. The amount of damage, Y, in thousands of dollars, and the distance, X, in miles between the fire and the nearest station are recorded for each fire. Assume that the linear regression model y equals beta 0 plus beta 1x plus epsilon is appropriate. Here are some summaries of the results. So we have here that the summation I equals 1 to the 15 fires of the xi's are equal to 49.2. I equals 1 to 15 fires of the yi's, and so on, 1 to 15 of the xi squareds, I equals 1 to 15 of the yi squareds, and I equals 1 to 15 of the xi yi's are equal to 1470.65. So what I'm going to do is I'm going to take each of these summaries and I'm going to put it into R. So we're going to start working in R on the left-hand side. Now, just as a refresher, when we look at our studio, we have our script up top. This is where we're writing our code. And then we have our console down beneath. You can think of the console as the brain of R. When you run the code, it's going to go into the brain and give you results. And then the environment tells us what objects are available to us. Since we haven't started anything, there's nothing over there. And that's how it should start every time that you open R. You want to make sure that your environment is empty. If your environment's not empty, one way to do that is to click on Session, and you can say Clear Workspace. And when you do that, that will empty your environment. And then we have the plot in the bottom right. Okay, so we've saved all these summary calculations. If you're on a PC, you can highlight what you want to run, and you can either press run or notice that it says Control Enter. If you're on a Mac, that's going to say Apple Enter instead of Control Enter, but I'm working on a PC right now, so that's why it's showing me Control Enter. That's the keyboard shortcut to run. So when I do this, I've now saved 1, 2, 3, 4, 5, 6 variables. And if I double check this right-hand side, it'll actually tell me what those variables are equal to. So I have a sample size of 15. The sum of the xi's is 49.2. The sum of the xi squareds are 196.16, and so on. So on this right side, this tells me what is in the global environment. If I use any of these values, they're ready to be substituted in. If there's something that I try to use that's not on this right-hand side, then I should be getting an error because R doesn't know what to do with the variable. Suppose I used a variable A. Well, A is not in the global environment. R doesn't know what A equals. So you're going to have to initialize A to be able to use it in your code. All right, I'm going to calculate the mean of X and the mean of Y. And once I do that, we should see that X bar is 3.28. We get the same 3.28 down here as we have on the right-hand side. And Y bar is 26.41333. So let's think about what this means. X bar, this is the average distance to the fire station in miles. So in our sample, the average home was 3.28 miles from the fire station. What does Y bar equal? This is in thousands of dollars the fire damage. So let's take 3 after the decimal, and we would say that the average amount of fire damage would be $26,413. Rounded. Okay, we can calculate the sum of the X deviations squared using the formulas in the book. The sum of the Y deviations squared, the sum of the X deviations times the Y deviations. These are all going to be helpful values for us to have. to calculate things like the slope and the y-intercept. Okay, for the slope, remember that's SXY divided by S dot XX, and we get a value of 4.919. So how do we interpret this in context of the problem? A 1 mile increase in the distance of the house to the fire station is associated with a $4,919 increase in the amount of fire damage on average, right? So if we think about a group of homes, one group of homes is 1 mile further than the station compared to the other group of homes, then we would estimate that there would be approximately a $5,000 increase, right, in the amount of fire damage in the group of homes that was 1 mile further from the fire station. So when you're doing city planning or you're doing other things, then people might think, hey, if the fire damage is going to be that much more, hey, maybe we need to have another fire station because the damage would just be too great because the firemen wouldn't be able to get to the house in time. And so that's how they could plan out how many fire stations that they would want to have. All right, remember that Y bar and X bar are guaranteed to be on the prediction line. So we can get beta hat 0 being Y bar minus beta 1 hat X bar. And when we do that, we get a y-intercept of 10.2779. It doesn't always make sense to interpret the y-intercept, but in this case, it would say for houses that are 0 miles from the fire station or very, very close to it, probably not on top of it, right? Very, very close to the fire station, right? The estimated fire damage would be $10,277. So that's similar to your baseline, right? If you're right by the fire station, this is the baseline. Then going further and further away, you're going to add the cost of being further away in addition to that baseline amount of fire damage. Okay, so if we want to create the prediction line and just have it spit out a sentence for us, we can give it the phrase y hat equals 10.2779 plus 4.9193 times x. Okay, remember that in this case, there's 2 parameters that are being estimated. That's our beta 1 and beta 0 are both being estimated. So we have 2 parameters that are estimated, and our degrees of freedom is going to be equal to n minus k. So since we had 15 houses, our degrees of freedom in this case is 13. We can calculate our sum of squared errors using the formulas as before. And remember, this is the same as the observations minus the predictions squared for each of the 15 houses summed up, and we get a value of 69.75. We can move on to get our coefficient of determination, which is r squared. And using the formulas, we get an r squared value of 0.9235. So the r squared is giving you the predictive power of the model. This is excellent predictive power because it's very close to 1 or very close to 100%. We could say that 92.35% of the variation in the damage in thousands of dollars, right? The amount of fire damage can be explained by the number of miles that the house is from the fire station. So distance from the fire station is an excellent predictor of the total amount of fire damage in dollars. We can calculate the correlation coefficient by doing the sign of beta hat 1. That's just saying was there a positive relationship or a negative relationship between X and Y? That's what the sign is pulling off. And then we're going to just take the square root of R squared. So we can get the correlation now. And the correlation is 0.96. That's very close to 1. So we'd say there is a strong positive linear relationship between X and Y, but we want to do this in context of the problem. So we'd say there's a strong positive linear relationship between the distance from the fire station and the amount of damage in dollars, right? As the distance increases, the amount of damage also increases on average, right? Both the slope and the correlation, notice they have the same sign. In this case, beta hat 1 was positive. And similarly, we see that our correlation is positive. So I hope you learned something today about coding and about R in general. You can choose to just use this exact code, or you could create code of your own that is maybe more straightforward or simpler for you to understand. You can also decide what you want to call each of your variables. If you wanted to call this s.xi instead of sum.xi, that would be completely fine. The only thing that I would suggest to do is that write your code so that if you looked at it in 6 months from now, without looking at it for 6 months, that you would be able to understand what you wrote, okay? So that can be a skill that you pick up over the semester or even over the next few years in general, but you want to be able to look back at your old code and say, what was I trying to do here? And one of the ways you can do that is by leaving yourself some comments like I have here. The pound sign is what tells R that you are just leaving yourself a comment. So here I reminded myself, hey, I'm calculating the mean of X. And now there's the calculation. So I hope you learned something today, and I'll see you next time.